Hi. So we're going now to finish chapter 2 with the following type of ODE, which is exact equations. Okay. So exact equation are of the form m of xy plus n xy dy dx equal to 0, or simply mxy dx plus nxy dy with equal to 0, with, this is a condition so that it's exact. Any first order ODE, by the way, you can write it in this form, but to make it exact, I should have this condition: m sub y equal n sub x. Okay. I.e., the field, if you recall, the field m n is exact, and hence the name of this type of ODE, exact equation. Now, the field mn is conservative in the form m dx plus n dy is exact, and this is where the name comes from. Now, how to solve it? So how to solve it? Now, given an exact equation, m dx plus n dy equal to 0, there exists a potential function f, a function of xy, such that nabla of f is equal, grad f is equal m n. Yes, this is from chapter 15. So given a function, you have m, you have a gradient field. I mean, given a function, given an exact ODE, this form m is a field mn is conservative. Since the field mn is conservative, there exists a potential function. There's infinitely many because they can differ by a constant, such that grad f equal mn. Then the curve, the solution to the ODE, then, let's say in a better way, then the level sets of f are solution to the given ODE. What is the, how do they look like? I.e., f of xy equal to c, where c constant, our solution. Proof? Well, given a level curve of f, i.e., f of xy equal to c. Now, seeing y, we're recalling y as a function of x, then I have f of x, y of x equal to c. Yes. Now, differentiating with respect to x, what do we get in this case? I get df dx plus df dy times dy dx equal to 0. This implies fx plus y prime fy equal to 0. But what is fx? Fx is m xy plus y prime, f sub y is n xy equal to 0, and this implies mxy plus nxy dy dx equal to 0, and this implies mxy dx plus nxy dy equal to 0. And this is my, and then check. Then the function y is satisfying f of x, y of x is a solution. Let's do an example. Well, let's do a couple of examples. Example. Verify that the following ODE is exact, then find, then solve it, and then here I put a remark: you can keep your solution in implicit form. Okay, so let's do the solution. So I have the ODE, well, what is the ODE? 3x squared y squared plus x squared dx plus 2x cubed y plus y squared dy equal to 0. So the solution of this plus x squared 2x cubed y plus y squared dy equal to 0. Okay, I want to check that this is exact, so I have m of xy equal 3x squared y squared plus x squared. What is m sub y? M sub y is 6x squared y. What about nxy? This is 2x cubed y plus y squared. What is n sub x? It's 6x squared y. I have m sub y equal n sub x. Then the above ODE, or the given ODE, is exact. So how do I find the solution? So the solution is R fxy equal to c, with where f is such that nabla of f, grad f is mn. Next, I need to find f. Well, we already did this in the previous section, yes, in chapter 15. So grad f is mn, which just means, so next we find f. So f sub x is equal 3x squared. Well, f sub x is m, which is 3x squared y squared plus x squared. And this implies that fxy, now integrate with respect to x, you get x cubed y squared plus x cubed over 3 plus some function that is independent, some constant that's independent of x, so it can depend on y, so I will say g of y. So then this implies that f sub y, now I need to find g sub y. How do I find g sub y? I differentiate with respect to y, and we get 2x cubed y plus g prime of y, and I want this to be equal to n, which is equal to x cubed y plus y squared, and this implies that g prime of y equal y squared, so g of y equal y cubed over 3. Then conclusion, well, plus a constant, and let's call this constant a. It's a different constant. Conclusion, I need only one potential, f of xy equal x cubed y squared plus x cubed over 3 plus y cubed over 3 is a potential function to the ODE, well, to the field Mn. So then the solution is solution R, because this is many solution, or x cubed y squared plus x cubed over 3 plus y cubed over 3 equal to constant. And these are all my solutions. Example, show that the following IVP has a unique solution then find the implicit form. Well, the IVP is y prime equal 2x cosine y over x squared sine y plus y of 3 equal to pi. Now, how do I prove that it has a unique solution? I write it in the form y prime equal f of xy. So here, little f, here I have y prime equal, I will write it h of xy. Why? Because I already, well, because I have already 2f now. I have f the gradient and I have f for the uniqueness. So I have y prime equal h of xy. And this implies where h of xy equal 2x cosine y over x squared sine y plus y. And h sub y, what is the derivative with respect to y? This will be equal minus 2x sine y into x squared sine y plus y minus x squared cosine y plus 1 times 2x cosine y, all this over x squared sine y plus y squared. Both of these are continuous in a neighborhood of 3 pi. Why? Check it. Since the denominator here at 3 pi, since I mean they are combination of continuous function and the denominator are different than 0, at 3 pi. Check it. What is the denominator here? It is 9 sine pi plus pi is equal to pi, and here the denominator is 9 squared, which is equal to 81. No, 9 sine pi plus pi is equal to pi, and this is pi squared. Okay. This is too much here. Pi squared. Okay. So it's different than 0. Then, by Picard theorem, the solution is unique, or the ODE has a unique solution y equal y of x for x in a neighborhood of x0. What is x0 here? Is 3. For x in 3 minus delta, 3 plus delta. Okay. All this to say that I have a unique solution. Now let's check what is this solution. Now looking at this ODE, you would think, is it linear? Definitely not. I have sine y, I have cosine y. There's a lot of reason why it's not linear. Is it separable? No, you will not be able to separate the x here from the y. And it's not homogeneous, because Euler homogeneous you can't write as y as a function of x. I mean, so you try the standard one that you already learned, but you will see that it's none of them. So your best bet now is to see if it's exact. But it's not written in an exact form, so I have to transform it into something in an exact form. So I have y prime is equal to x cosine y over x squared sine y. So you see this thinking I did, it's not separable, it's not linear. You should do it yourself, okay, every time you see an ODE. So this is dy dx equal 2x cosine y over x squared sine y plus y. So this implies that 2x cosine y dx minus x squared sine y plus y dy equal to 0. Now let's check if it's exact. I have m of xy equal 2x cosine y. So m sub y is minus 2x sine y. What about nxy? Nxy is minus x squared sine y minus y. So n sub x is minus 2x sine y. I'm differentiating with respect to x. So m sub y equal n sub x, then this is exact. Now it's an exact ODE, so then the solution are of the form fxy equal to c with grad f equal mn. Now finding f, I have f sub x is equal to m equal 2x cosine y. Now integrate with respect to x, you get fxy. What is the integral of 2x cosine y with respect to x? Is x squared cosine y plus a function that is independent of x, h, well, g sub y. What about f sub y? Now differentiate with respect to y. So f sub y is minus x squared sine y, because the derivative of cosine y is minus sine y, plus g prime of y. And I want this to be equal to n, which is minus x squared sine y minus y. And this implies that g prime of y equal minus y. So g of y equal minus y squared over 2. So therefore, plus a constant. Plus a constant a. Therefore, I'm choosing a to be equal 0. If you want, choosing a equals 0. You can choose a whatever you want. Doesn't matter. Choosing a equals 0. F of xy equal minus x, equal x squared cosine y minus y squared over minus y squared over 2 is a potential function. Is a potential to mn. So then, therefore, the solution of to the ODE, the solutions to the ODE are x squared cosine y minus y squared over 2 equal to constant. But now I have an initial condition. But, okay, now since y of 3 is equal to pi, replace in the solution. What do you replace in the solution? You replace this is x and this is y. So you get 9 cosine pi minus pi squared over 2 is equal to c. And this implies that minus 9 minus pi squared over 2 is equal to c. Okay? Now that's it. I mean, that's then the solution. So conclusion, the solution, the unique, I already know that's unique, the unique solution to the IVP is x squared cosine y minus y squared over 2 is equal to minus 9 minus pi squared over 2. And that's my solution. Okay. I will end this part now of the lecture. And next we're gonna deal with equations that are not exact, and we're gonna learn how to transform them into exact equation in special cases.